All right, so f of x equals 0 to x sine t dt. That's it. Yeah, so I would say quickest thing to do for continuity. Let's say xn goes to some x. So let's say we want to prove this is so this is an L1 of 0 to 1. Matter that much. Oops. Nothing special about that, really. Well, I guess if you want to do absolute continuity, you could really do that on a real line, but typically do that on a closed interval. All right, so assume this is in 1, and this is in 1. Okay. Let's say yeah, let's say let's say Fn is simply f of t times characteristic function of 0 to xn. So that means, yeah, it is definitely a trick you gotta like nail down. So big F of xn would be what? Or maybe just make things a little more efficient. Let's stick a sine t in there. So big fxn, I mean, we want to prove big fxn goes to big F. That's continuity for each x in 0 to 1. So I use sequential criteria of continuity. F of xn has to go to f of x. Big F of xn has to go to big of f of x for any sequence xn converging to x in 0. So big F of xn is going to be equal to what? Which is going to allow me to use trivially use or very easily use the dominated convergence theorem. The big F of xn is going to be equal to what? Well, it's just the integral of fn. Because this equals so you're integrating characteristic function. Right. And characteristic function just cuts it off to 0 to xn. And this is exactly what f of xn is. So is that okay? Everyone kind of see? Everyone okay
Yeah, it
with
makes
that?
sense.
Sorry?
It makes sense, yeah.
Yeah. So, and the dominator, there's nothing really to the dominator. It's just, well, it's just less than or equal to f absolute value. Because characteristic functions between 0 and 1, signs between 0 and 1, an absolute value. So yeah, and make sure this is actually right. I mean, just making sure the characteristic function converges properly. So you can certainly say this limit here. It's characteristic function 0 to x t something t. You want to be a little. I mean, you're not quite. It's not really clear at t equals x if you have convergence, because you can have a few different situations. I mean, it doesn't matter because it's just one point. But let's say here's x. So you could have like the xn's kind of like converging like this. You could have it kind of oscillate like here, 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 here. Yeah, so so it's a little iffy at x, but certainly this is true almost everywhere. So I mean, particularly yeah, I mean, particularly for any point in 0 to 1 other than x, this is certainly true. I mean, it could be true at t equals x. Yeah. So you definitely know this is true. This. All right, so particularly dominant convergence theorem gives me exactly want. So this is this limit. Yeah, so it's going to be this here, f of t, and that's just big F of x. Here to x. Sorry, t. Yeah, so that would prove yeah, that would prove convergence. Sorry, that would prove continuity. Now, if you want to do absolute continuity, I did mention this, and I'm actually going to do a final video on this today, hopefully today. So at the very last extra class, I mentioned a fact that's actually pretty easy to prove using particularly density of step functions in LP. So you could use Borel-Cantelli also to do this. So if G is an L1 of any E, any measurable E. Epsilon is bigger than 0. Then there exists delta bigger than 0. So for any A, it's a subset of E, measure of A less than delta implies that this is less than epsilon. So not a terribly surprising fact. Yeah, okay, so absolute continuity. We just have to go back to the definition, really. Enter that. Okay, so to prove definition. Yeah, so the prove for any epsilon bigger than 0. There exists delta positive, where for any disjoint collection of intervals AI, BI. And here N can be either, so this is slightly different than the book's definition, but basically in a homework, the book proves that it's equivalent to this. So N could be either a positive integer or it could be infinity. I mean, either way. There's a collection of intervals in A to B. With the property that this is small. We have this sum is small. So if this sum is small, then this sum is basically small. And to get this sum to be small, we just have to set this to be really small. Right. Yeah, so let's pick basically intervals. Yeah, pick intervals like this, where this is true. And I want it to correspond to let me this. Before meaning here. E here is 0 to 1. And G is just f of t sine t. It's certainly now 1 because f is an L1. F is integrable. Yeah, f is Lebesgue integrable over 0 to 1. That's what the problem says. Yeah, okay. So our task is to show that this sum here is less than epsilon. So let's just see what this is. 0 to what's the absolute values here? 0 to BI. Minus 0 to AI. Yeah, and so this is going to be equal to what? I can't really fit it here. The absolute value of what interval? From what to what, particularly?
AI to BI.
Yeah, this is AI BI. We don't even need the sine t. We can just do the f of t. Sorry about that. I mean, sine t also works, but so just smash in absolute values. BI. Oops. Okay, so we're assuming this is part of our yeah. Well, I didn't write it down, but I did. So we're assuming this is a disjoint, pairwise disjoint collection of intervals. That's part of what we are allowed to assume. And yeah, if you didn't come to, or if you're not familiar with absolute continuity or forgot about it, one thing to be clear is that this is like super duper continuity. In particular, like when n equals 1, we get absolute continuity implies regular continuity. That's just saying if you have any a to b where b minus a is less than delta, that would imply for small enough delta, the absolute value of f of b minus f of a, or sorry, we have anything in a to b where this is true, just for one single interval a to b, it's a prime to b prime, then this is true also, or this implies this for just one interval in a to b. Yeah, big N equals 1 gives you continuity. Yeah, so let's say A is this disjoint union. So the measure of A is the sum, which is we assume to be less than delta. And so this sum here sorry, big F. So yeah, we estimate each one of these. So now I'm just going to sum up over all of these. But we mentioned was the end of the semester that integration behaves like a measure. So this is going to be equal to what, which basically finishes the proof. So this is going to be equal to what? So what would this be equal to? The integral over what set? Number. So this sum is going to be the integral over what set?
Would it be A?
Yeah, it's just A. And that's less than epsilon, because that's how we made sure that and we picked delta corresponding to F here. We set G to be F. I guess we could just do F here. Could even just do that. Kind of silly. Yeah, I mean that's basically that's it. We picked delta where this is true. And that we picked the same delta here. So then if this is true, or these are disjoint intervals in A to B, then you just, by the nature of integrals, less than equal to this, sum up. So it's integral over A, and it's less than epsilon. Yeah, so we this is kind of analogous to what we did in that last extra lecture, where I proved kind of the trivial half of the very deep theorem that I think it's from actually Lebesgue himself. It's proved in the book, but it's a long proof, like it's probably hard. I'll say harder than anything we've done in the course, but that a function is absolutely continuous if and only if the fundamental theorem of calculus holds for a where the derivative is integrable. So in particular, the same proof proves the following, that if you have a function where f prime is an L1, it would be, and if this is true, you would hope is true, if you forgot how to do this, it's a good exercise because it's basically the same thing as what we just did. Except the f of a's cancel out. B. Then f is absolutely continuous on A to B. Yeah, so what is it? Yeah. So to be clear, what is extremely hard to do, but a very deep classic result analysis is absolute continuity implies fundamental theorem of calculus, that f prime exists, it's L1, exists almost everywhere. I can't do better than that. It exists almost everywhere, it's an L1, and fundamental theorem of calculus holds. Yeah, any questions on this problem?
I didn't quite catch exactly how you chose delta.
Sure. So this is like a little fact. I don't think I gave it for homework. But this is a fact. And we can even maybe not this time, but maybe next time we can go over proving this. But I'm pretty sure this was itself a prelim problem. But yeah, so literally pick delta from here. So for any epsilon bigger than 0, there exists a delta where this is true. Okay. And I'm claiming that this delta here is what works for proving absolute continuity. That's where I get delta from this fact.
Thank you.
Yeah, sure. Yeah, okay. Any other type of problem me to go over? Anything from here you want me to go over? This last call. Basically anything from any prelim that's not on the do not do list. All right. I mean, yeah, I guess I'll end for today. Yeah, I mean, do try and come next time with some questions. It could be anything you want to review or any. Because I mean, basically going over like from start to finish, that's almost like going through like half the course. Like I would probably need like 3 hours a week, like basically half of a semester to like go through everything. So I can't really just go through everything. I really have to do what you guys want me to go through. All right, so yeah, I expect an email today about some videos. Just updating the kind of playlist. And yeah, all right, I'll see everyone. We'll see some of you Thursday. I mean, obviously I'm not offended if you don't come, but yeah, I'll see some of you guys Thursday. Take care.
Thanks for doing this.
Yeah, sure thing, no problem.
Thanks.
Yeah, and definitely do give me a day in advance for the problems, because I mean most of them I've done, but as you guys, some of you witnessed last time, there is the occasional problem that I kind of realize, oh wait a minute, this is a lot. This is not as quick and easy as I thought it would be. So
Yeah, I'll try to find some more for next time. I
Yeah.
was expecting these to be in person, so I wasn't expecting to be able to attend.
Oh sure, that's fine. Yeah. All right.
See ya.
Yeah, take care.